So the last law of thermodynamics is the third law of thermodynamics, which means that you can't reach absolute zero. That means on the Kelvin scale that you will never reach 0 degrees Kelvin. Okay? So on the Kelvin scale, it's impossible to do that. And that kind of goes a couple of ways why that's true. The first reason is that when we talk about temperature, we talk about kinetic energy, right? We're talking about the motion of that particle. So the colder and colder and colder you get an object, the less and less it has kinetic energy. It keeps going down and down and down and down. What ends up happening when you start approaching that basement level is that you have very, very small motions going on. But you're no longer talking about the sheer randomness of a particle. You're looking at that particle in a completely different light when you're talking at low temperature. You're looking at it through the eyes of quantum mechanics. So as you're reducing it down closer and closer to zero, the properties of that particle become strange, become very strange, as a matter of fact. When we start looking at it, you're trying to measure its velocity, its kinetic energy, and as you're trying to measure something that's so small, you get a breakdown. There's a law called Heisenberg's uncertainty principle that says to a degree of measurement, you can only measure the position to a certain amount, and how accurate measure that position affects on how accurately you measure the velocity. And the truth of the matter is, it's not just about measurements. If I measure the position of that particle with a high degree of certainty, its velocity is really, really big. Okay, so it's this exchange. I mean, if you think about it this way. So here's its position, and here's its velocity. Okay, and it's not velocity; it's momentum, actually. And we've already talked about momentum, So if I measure my position with the high degree of certainty, okay, which means that it's not in this range, it's now in this range, my momentum goes up considerably. And there is a direct relationship between position and momentum. So the act of observing that particle, that object, affects its position and it affects its velocity, its momentum. Okay? So when you're measuring thermal properties, you're zooming in on that particle, that slow-moving particle, and you're affecting its momentum. You're affecting its position, too. So you're getting all of these insane things happening. So you get a breakdown, okay? So, and I'm not happy with this answer I'm giving you, but that's basically what's going on. It's impossible to measure its velocity with a high degree of certainty. If you do, the location of the object is boom, anywhere in the universe. Okay? It goes everywhere. So the problem is how do you do that? How do you go in there and say, well, look, it only has so much kinetic energy. Look at that. Its momentum, because remember there's a relationship between energy and momentum. That momentum of that object is zero. Well, if that's zero, then what does that turn into? Okay? So that's why it's impossible for an object to achieve 0 degrees Kelvin. It's impossible. It cannot be done because of the Heisenberg uncertainty principle. Okay? So that is the third law of thermodynamics. If you want to talk more about it, you please approach me in class. I mean, this stuff is kind of fascinating. I've really gotten an appreciation for the Heisenberg uncertainty principle in the last couple of years, which, you know, my old college buddies would probably give me a really hard time about that. So, sorry. That's third law of thermodynamics. Thank you.